Thanks for watching, and here is the most important example of the Fourier transform. Namely, today we will calculate the Fourier transform of the Gaussian function. In other words, if you take the bell curve and you apply the Fourier transform to it, what will you end up getting? And the answer will surprise you, I promise. So here, let f of x be e of minus x squared. And what we want to find is the Fourier transform of f, which we'll write f hat. Usually it's written f hat of xi, but I can't write xi, so let's use kappa. And which now here is the integral from minus infinity to infinity of f of x times, some people use e minus I kappa x, but for simplicity I'll use e of I kappa x dx. And sometimes there's a factor of 1 over 2 pi, but again, they're all equivalent in the end, so we'll just use the simplest definition. And so in particular, concretely, what we have to calculate is the integral from minus infinity to infinity of e of minus x squared e of I kappa x dx. Now, one way of calculating this is simply to complete the square and recognize it as a Gaussian, but why do that if you can do it the swag way? So I will actually show you now the cool Dr. Payam way of doing that. Because our goal now actually is to find an ODE for f hat. So step 1, find an ODE for f hat. Because you'll see there's a cool self-replicating phenomenon that's happening here. So let's take f hat of kappa, and to find an ODE, let's differentiate this with respect to kappa. So it's d over d kappa, dk, Donkey Kong, of the integral from minus infinity to infinity of e of minus x squared, e of I kappa x dx. And now, I'm going to do something that's quite illegal in math, but I'm going to do it anyway, because I'm cool like that. Let's put the derivative inside the integral. And just FYI, this is justified actually using what's called the dominated convergence theorem. See, this goes to 0 very fast, and that derivative you can replace with difference quotients, and you can show that actually it's legit what I'm doing. And so, what we get then, this is the integral from minus infinity to infinity of the kappa derivative of e of minus x squared, e of I kappa x dx. And the point is, this thing is a function of x, so it acts like a constant. And so this function also gets out of the derivative with respect to kappa. Again, because this is constant with respect to kappa. And so what we end up getting is integral from minus infinity to infinity, e of minus x squared, d over d kappa, e of I kappa x dx. And then you just have to differentiate this with respect to kappa. So in other words, this ix comes out. And so what we end up getting is integral minus infinity to infinity of e of minus x squared, ix, and then e of I kappa x dx. And let's just rewrite this a little bit. So let's put this I out and then combine the x and e of minus x squared to see what we get. So step 2. What have we found so far? So d over d kappa of f hat of x. So there was an I that came out, and an integral from minus infinity to infinity of x e of minus x squared, and then e of I kappa x dx. Now notice, this is a product of two functions. This can be integrated easily, this can be differentiated easily, so it's really time to use an integration by parts. So integration by parts, don't break our hearts. So this will be your dv. dv is x e of minus x squared, times dx if you want. This will be your u, is ei kappa x. And then v, c'est la vie, is integral of x e to the minus x squared. You can use a u sub if you want to get minus 1/2 e of minus x squared. And then for u, you just differentiate with respect to x. So u is ei kappa x, and so du is ei kappa x. So after you integrate by parts, you then get that this is I, and then, so minus 1/2 e of minus x squared, e of I kappa x, from x from minus infinity to infinity, and then minus integral from minus infinity to infinity of minus 1/2 e of minus x squared, and then I kappa, e of I kappa x dx. Okay, and now let's analyze this a little bit. So this function e of minus x squared, it goes to 0 very quickly. In fact, it literally goes to 0 like e of minus x squared. You know, that's how fast it goes. Okay? Now, e of I kappa x, that is cosine of kappa x plus I sine of kappa x, that term is bounded. So it never goes above 1 in absolute value. So that's what's called bounded. So it's kind of a term that doesn't go to infinity, and you multiply by a term that goes to 0 very fast. So this whole thing goes to 0. And by the way, this will always be true for the Fourier transform. Whenever we take a Fourier transform, you can always assume that the terms at plus or minus infinity is 0. Why? Because those are the functions that we'll consider. We'll only consider functions with that property that goes to 0 very fast. Now, for this, notice this term comes out, the minus 1/2, and the I kappa comes out. And so what we get, minus 1/2 is plus 1/2, and then this I kappa comes out. And so in the end, what we end up getting is, so the derivative of f hat, so we had an I from outside the parenthesis. So minus 1/2 is 1/2. And then we have an I kappa. And then that integral from minus infinity to infinity, e of minus x squared, e of I kappa x dx. Now this thing just becomes minus kappa over 2. But most importantly, what is that integral equal to? We take f, we multiply by ei kappa, and we integrate. This is none other than the Fourier transform. Wow! So in other words, there's almost a fractal phenomenon going on. If you differentiate f hat, then you get this number times f hat itself. And this is really the essence of differential equations. When you differentiate a function, do you have the same function appearing, right? And if yes, then there must be something nice going on about this function. And so we end up getting this ODE, d over d kappa f hat, plus, if you want, kappa over 2 f hat equals 0, which is an ODE. And in fact, this is an ODE we can solve, so that's the point of the next step. So I think step 3 or maybe step 4. Well, notice this is similar to an ODE we've done in our ODE class. Namely, this is the same thing as y prime plus t over 2y equals 0, which is really of the form y prime plus some function of ty equals 0. And remember, to solve this, all you need to do is multiply by an integrating factor. It's a trick. Multiply by e of integral p of t dt. So integrating factor. And in fact, let's do this for our differential equation. So we have d over d kappa f hat of kappa plus kappa over 2 f hat of kappa is 0. So here, what is the integrating factor? So e of this integral, so kappa over 2 d kappa, which is e of 1/2 kappa squared over 2, which is e of kappa squared over 4. And remember, we just need one integrating factor, because if you add a constant to it, you will see it will cancel out here. Okay, so let's take our ODE and multiply by e kappa squared over 4. So we have d over d kappa f hat plus kappa over 2 f hat equals 0. And once again, let's multiply this. E of kappa squared over 4 times this is e of kappa squared over 4 times that. Now, by the integrating factor method, and you can review the proof if you want, this whole thing just becomes the derivative of the factor times your function. So this is the same thing as d over d kappa e of kappa squared over 4 f hat, and this becomes 0. And again, it seems like magic, but not really, because that's how we chose that integrating factor. Very good. So what we know is this function has 0 derivative, so it's constant. So e kappa squared over 4 f hat of kappa is constant. And so what is a Fourier transform? Well, it's c e to the minus kappa squared over 4. That said, in our grand finale, we can do is even better. Let's actually find this constant. So last step, what we found so far is f hat of kappa is c e to the minus kappa squared over 4. But the question is now, what is c? What is c? Baby, don't hurt me no more. Because this is true for every kappa, so let's now let kappa equal 0. Then what you get is, well, f hat of 0, that's c e to the minus 0 squared over 4, but that becomes c. So reading it Persian style from right to left, or Arabic style, we get c is f hat of 0. And remember, the definition of this is the integral from minus infinity to infinity f of x e to the I 0x dx. And so this becomes the integral from minus infinity to infinity of f of x dx, which is the integral from minus infinity to infinity of e of minus x squared dx. And lo and behold, this becomes the Gaussian. So by the Gaussian integral, that is square root of pi. Which is kind of cool if you see the videos in order, because the previous video was a Gaussian integral. So in the end, the Gaussian integral reappears. And so what is f hat? Well, that's c e to the minus kappa squared over 4, which now becomes square root of pi e of minus kappa squared over 4. Which is so cool. In other words, the Fourier transform of a Gaussian is again a Gaussian. And in fact, this is really, you will see, the essence of how we will be able to solve the heat equation. If we didn't have this reflective phenomenon, then we may not have an explicit formula for the solutions to the heat equation. Last but not least, I just want to generalize this. So what have we seen? We've seen that the Fourier transform of e of minus x squared becomes square root of pi e of minus kappa squared over 4. Well, the same thing holds true if you do e of minus 3x squared, for instance. In fact, the fact is the Fourier transform of f of x equals e of minus ax squared, let's say where a is positive, is f hat of kappa. So I believe the correct scaling is square root of pi over a e of minus kappa squared over 4a. Which is really a fact that we'll use a lot when we solve the heat equation. Alright, I hope you like this Fourier extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.